Hello. I'd just like to explore Riemann a little bit more and to show again what it means utilizing the particular values. Um, Again, please refer to this very important video that I've done, Math Paradox Finally Explained, on YouTube, that shows why ratios work but division does not. It's very important to understand. I'll briefly go over it. Also, for the values of Riemann that I use in this example, I just come over to here, this table. And basically, so I'm going to just briefly go over the paradox problem of why division is just giving us values in the 10 system and not the true values. And because 1 over x is the problem, because 1 over x only works for 1 over 1 to get back 1. Or if it's a 0 and we look at it like a ratio instead of a division process, then 1 sliced up 0 times would give you back 1. But division-wise, 1 over 0 is undefined. So 1 over 1 equals 1 in math. And that's represented by this point divided by that point, and it preserves unity. But when we do 1 over 9, 9 never goes into 1. Or 3 never goes into 1. Or only 1 goes into 1 in the language of division. So we get a 0 there. And that's just the concept that if we have 9 and I try to put it into 1, I'll get a 0. But if I put 9 into 10, it goes in 1 time. And then I have 1 left over. And from that 1 left over, by the language and the convention, we create another 10. And then 9 goes into 10 one time. And 9 goes into 10 one time. So we get this. And if we multiply 9 by this, we get back 0.999999, but we never get back 1 because 9 never went into 1 in the first place. So 9 goes into 10 one time, or 9 goes into 111 times, or 9 goes into 1,111 times, or 9 goes into 10,000, 1,111 times. But it never went into 1, ever. And that's why the proof 1 equals 0.99999 is not true, because it's not getting us back to this. This concept is being avoided. And that's the foolery of the language, because 1 does not equal 0.9999999. And now when we look at Riemann functions, and for the values, which I took off of this chart, so for Riemann value 2, if we do the expansion out to infinity, and it converges, quote unquote, onto this value, pi squared over 6. Well, now we're dealing with pi, which is not an integer. Pi is not an integer, so there's no way to deal with pi and get back a 1 or a 2 or a 3 or a 4. It's not possible, because pi in relation to 1 is this value. The only way to get back pi, the integer, is to do pi over pi. That's the only value where I'll get a 1. It has to be in relation to pi. So these are mixing up values. So if we get this value, pi squared over 6, we can look at this. First, we could look at 1 over pi, for example, would be about 3 into 1, And again, that doesn't work. But 3 goes into 10 because this is now the 10 system over here 3 times. The same thing with the pi squared. We get the same situation where 1 in relation to pi squared, well, pi squared is about 9. 9 never goes into 1, so we go 0. And 9 goes into 10 one time, so we get a 1 there. And this is the relationship of pi squared as related to 1. And we get this value. But it's non-integer value. There's no way to get an integer unless we do this relationship where we do in terms of a pi squared, because only a pi squared related to a pi squared can give us back an integer. Or if we use this value, then only a pi squared over 6 divided by a pi squared over 6 can give us back the full 1. There's no other value that can give us back 1 except for this value. This is the only value that can give us back 1. Pi squared over 6 over pi squared over 6. This is the value. Any other value, we will not get 1. This could also be written as pi squared over 6 times 6 over pi squared equals 1. So basically, the only way to get back this value, to get back to unity, is to use that value itself. Or if we just say pi squared over 6 and then do nothing to it, which would be pi squared over 6, and the concept of adding 0 or dividing by 0, even though 0 is not doing anything to it, we would just come back to pi squared over 6 itself. So any other term of pi squared, it's either pi squared over 6 is going to give us pi squared over 6, or pi squared over 6 over pi squared over 6 will give us 1. Any other value will not preserve any type of unity. We have to speak the same relationships here. Integers and pi can't get back to an integer unless we put pi in relationship to pi and get back our integer. So if we look at this specific value of Riemann at 2, we get pi squared over 6. And that, then when we take it to convert it into an integer system that's based on 10, we come up with this value, 1.6449, when we calculate it out. Because as we've seen before, pi squared is about equal to 9, and 6 goes into 9 one time. But 6 never goes into 1. So the only reason this works is 6 goes into 9 one time. And this is the value that we get when we calculate it out. And so the only way to converge would be to take this value, pi squared over 6, and multiply it by the only value that will give back unity. And I'm going to multiply the other side by that same unity value. And what's it going to do? Well, this will then cross out and get to 1. And then this term is going to be 0 taken out to infinity. If I continue this decimal, but if you multiply this out on your calculator, you will get 0.999999. We have the same problem as before. We can't get back unity because the only way to get back unity is to use the relationship in terms of this language is now, this is relative to 10, this value, and this is relative to a pi squared over 6. So we're trying to do integers in relation to pi and get back some kind of value, which is impossible because pi related to an integer can't give you back an integer, or pi squared related to an integer cannot get you ever back to an integer. It has to be pi relative to pi. So for these values, when I do these reciprocal multiplications of both sides, for every value of Riemann, I'll get 1 equals, and then that's the next value, and I multiply it by the reciprocal on both sides. I get 1 equals 0.9999. When I carry this out, you could check this out on a calculator, and it's the same issue as this issue. When I multiply this term by 9, I get 0.999999, because the two are not related to each other. They're not speaking the same language. They're not relative to each other. One value is relative to a pi value, and the other value is relative to a 10 value. So there's no way ever to get back exactly 1. So the best we can get back are these kinds of terms. So again, we have the same issue, that 1 over x is a problem in mathematics. When we do a division, we can't get back to unity when we try and divide something into 1 other than 1 itself. It's the only time we can get back to 1. So this is why Riemann only values can approach 1 or infinity and 0, because the language of 1 in math, the concept 1 over 0 doesn't exist. It comes back as a an empty set. The same thing, 1 over 1 means complete infinity. Again, please refer to my math paradox lecture to see why this holds true. But this is Riemann in a nutshell of why it can't work. It says it converges to this, but it doesn't. It converges to this value, and we get the 1 equals 0.999, the same proof of this. And this is not true, because this is related to 10 and this is related to 1. If you refer to the paradox video, you can see what I'm talking about. And so Riemann is just this a repeat of the same problem within the language, or rather the interpretation of the language of mathematics. The next lecture, or you can please refer to the lecture on non-duality for the explanation of why math is avoiding the non-dual states. And it's because of the issue of the language. Math and the other sciences are observational in nature, and this causes a problem when we go to define the entirety state of something or the complete nothingness state of something. So thank you very much for your time.